Hi, good morning everyone. Today we are going to discuss about the EMI filter for high frequency power converters. Come, let's get into the topic. So, with the improvement in power MOSFET technology and the development of high frequency PCB power transformers, it is now possible to design power efficient isolated converters in megahertz frequency range. Frequency spectrum. The analysis of frequency spectrum of 200 kilohertz PWM, that's a pulse width modulation converter, reveals the most of its conducted noise is at 200 kilohertz and some at multiples of 200 kilohertz. Similarly, the converter switching at 2 megahertz frequency has most of its conducted noise at 2 megahertz and some at multiples of 2 megahertz. The input EMI filter has to be designed to maintain the harmonics, the amplitude of all harmonics appearing in the frequency range of 150 kilohertz to 330 megahertz within CASPR limits. So this is the frequency spectrum which shows the x-axis as relative frequency in hertz and y-axis power in dBm. So H of ceramic input capacitor, that's the components. EMI filter having the following components. The first and primary thing is H of ceramic input capacitor. It reduces the WSW ringing, improves greater than 10 megahertz. Bulk capacitors. ESR damps resonance with filter components less than of 1 megahertz. CLC LCL pi by T filter filters up to 10 to 100 megahertz. Ferrite weight filters greater than 2 megahertz specified at 100 megahertz. Common mode choke filters common mode noise up to approximately 100 to 300 megahertz. So this is the circuit diagram of common buck input filter components. So active EMI filter uses an op-amp to replace passive CF with active capacitor. So the replacement which is shown in the circuit diagrams here. So active EMI filter uses an op-amp to replace CF with active capacitor. Op-amp gain term, that is GOP, approximately CSEN by CAEFC, where CSEN is the AEF sensing capacitance capacitor and CAEFC AEF compensation capacitor. And again, the next thing, active filter LIN and CNJ selection. This LIN CINJ, which is equal to 1 by GOP 2 pi FC whole square, where CINJ is the AEF injection capacitor. With GOP equal to 100, filter can reduce LF and CING 1/10 compared to passive. Input voltage and current ripple causes EMI. Lowest ripple will result in lowest EMI. Capacitive sensing and injection. So no DC current into AEF. AEF ripple current cancels ripple current of input inductor. AEF is not limited to DC power rating. Limited to delta INJ cancelling delta ILN. So LIN or CIN can be sized to meet del INJ requirement. So here jitter, transients or any other permutations can cause an undamped response of our LC filter. CIN and LIN can resonate from regulator permutations. A damping capacitor CIND with ESR or resistor RIND is a parallel with CIN for damping. AEF can be purely capacitive and resonate with LIN if damped. This may cause saturation and increased power loss. So this is the traditional passive layout, uses a taller inductor and larger capacitors. Active EMI filter uses smaller and cheaper components with improved filter performance. Here the various graphical representation is shown over here. This first graph is no EMI filter. and second graph passive EMI filter, and third graph is active EMI filter. So when these cases are placed, so different responses we are getting for the different filter sections. So that is shown over here. Active EMI filter consideration. So root SEN and INJ traces differently. Place RAEF DEC at SEN and INJ bias, and C damp and R damp, RINC and CNC, CSEN close to AF compensation, CINJ close to damping. At op amp IC, AF amplifier VCC deep coupling capacitor close to pin, AF amplifier AVSS grounded on white ground. Thank you.